Alright, so today we are looking at generators and relations. Let's write that out here. I didn't quite screen this chapter, so I don't know how much of this is going to be new or not. Hopefully it's all fairly new. So we're still working with a semi-simple Lie algebra over an algebraically closed field of characteristic 0. And our idea is we want to find a presentation of L So we want a presentation of L of our semi-simple Lie algebra by generators and relations which depend only on our root system. And this will of course give us that for every root system has a unique semi-simple Lie algebra. And we note here L may be infinite dimensional. Because I know you can extend a lot of the Dynkin diagrams past what we saw before. They don't terminate in the dimensional, in a dimension, the semi-simple Lie algebra they describe, but well, that's what we're getting into here. First chapter is relations satisfied by L. So we're going to let L be a semi-simple Lie algebra with a Cartan subalgebra H, which gives us a root system of L on H, and a base of that root system as always. Recall that the angle bracket of two roots alpha I and alpha j is 2 times the form of alpha I on alpha j over alpha j on alpha j, which is equal, that's not where that parentheses goes, which is equal then to alpha I of h of alpha j, which we write as hj. Fix a standard set of generators xi in each L alpha I, yi in L negative alpha I, such that these are from our base too, these alpha I, such that the bracket of each xi with yi is equal to the corresponding hi. And this gives us our first proposition. With the above notation, I guess I'm not even going to write that out. L is generated by xi, yi, hi for range, because we have alpha as a collection of alpha I from 1 to L, and here I is going to be 1 to L. With at least the following relations. relation 1 is that the bracket of any two h's is going to be 0. Relation 2 is that the bracket of xi and of an x and a y is going to be, oops, sorry about that. It's going to be the index. If they share an index, it's going to be h of the index they share. If they don't share an index, it's going to be 0. We have 3a, which is the bracket of hi and yxj, is the angle bracket of alpha j on alpha I, scaling xj. B, likewise, hi on yj, scales yj by negative alpha j alpha I. We have 4a, which states that the adjoint of x of I to the negative alpha j comma alpha I plus 1 of xj is 0. And B, which is the same thing except with y instead of x. In the proof, we know L is generated by the xi and yi from a previous proposition, and we already know we know 1, 3a, and 3b, and we get 2 as alpha I minus alpha j is not a root when I and j are distinct, even when they're not distinct. When I is not j. Now we're going to show for A getting for B by symmetry. And this is, of course, these are both I not equal to j. Since by assumption I is not j, alpha j minus alpha I is not a root, and the alpha I string through alpha j is alpha j plus alpha I up through alpha j plus q alpha I, where q is the negative alpha j alpha I. Now, since the adjoint of xi maps xj along these root systems along the root spaces for is considered alpha j plus alpha I, all the way through alpha j plus q alpha I, and then plus 1 is going to be end up in 0. And so we are done. Now these relations only rely on the root system, involve constants only which come from our root system. And we will see these form a complete set of defining relations for L. Which is going to be a fair bit later on. But first we will look at the Lie algebra defined by our first three relations here. So consequences of relations 1 through 3. So we're going to pick a root system, I'm guessing an axiomatic one, phi with base delta, consisting of alpha I from 1 to L. Recall the Cartan integers. Man. Recall the Cartan integers are like Cij are defined to be equal to the angle bracket of alpha I on alpha j. Begin with a free Lie algebra L hat on the 3L generators xi hat, yi hat, and zi hat for I of 1 through L, of course. We're going to let K be the ideal and L generated by, well, our first rule is that the bracket of A2 and E2H's is 0, so we have the bracket H hat I, bracket H hat I with H hat J. Our second rule is that the bracket of xi and yj, we want this to equal delta ij of hi, so if we subtract out delta ij of h hat I, this should always be 0. And likewise with the Cardano integers, we can write h hat I x hat j minus the Cardano integer Cij times x hat j, and h hat I with bracketed with x hat j plus cji. Oh, this should have been, the other one should have been cji too. cji, and this should be a y hat j. We're going to set L naught to be L hat over K hat. With the image of our generators having images xi, yi, hi. This is all still a bit too nebulous to do any concrete work on L0. So we want to build a representation. And this is, it says the prototype of the one which plays a prominent role in chapter 6. Here's the pay attention. There's no problem about constructing a module for L hat, as we only need to specify a linear transformation for each of the 3L generators. Let V be the tensor algebra, also known as the free associative algebra, on a vector space with a basis of Vi from 1 to L and then make it a module. So we're just going to drop the existing product. And we're going to also, we will drop the tensor when writing products. We know we have our basis over V as the set of the products of vectors. Now we're going to define endomorphisms of V follows. The action of h hat j on 1 is going to be 0. And the action of h hat j on the product of a bunch of VI's, Vi1 times through VIT is going to be negative of Ci1 on j plus through to Cit, comma j on Vi1 through Vit. The action of y hat j on 1 is going to be Vj. The action of y hat j on a series of vectors vi1 through vit tensor product, we don't write it out as, is going to be correspond to this multiplying by vj. And lastly, we have x. We're going to have x hat j on 1 be the same thing as x hat j on a single vector, which is going to be 0. And then for multiple vectors, we want x hat j acting on vi1 through vit as going to be vi1 of the action of x hat j on vi2 through vit minus delta I1 times j. Delta, actually matching up I1 and j of ci2j plus through cit of j times the product of vi2 through vit. Then there is a unique extension to L hat of this action by its generators yielding a representation calling phi hat of L hat to the general linear Lie algebra of V. And that brings us to our next proposition. Let k0 hat be the kernel of this representation. Then our k hat factors, then k hat is within the kernel, so our phi hat factors through L naught, which is going to make V and L0 module. Now proof. If you look at H hat, it's a multiplier. It's just scaling, so H hat j acts diagonally on V relative to the base, relative to our basis, of course. So you bracket the representation of hi and the representation of hj are going to commute. So the bracket of h hat I and h hat j lies within the kernel of our phi. Also, as I mentioned before, without even looking at the proof yet, phi of y hat of j is left multiplication by v of j. Setting j to be I1, we get that x hat I on v hat y hat j on the product of vi2 through vit minus y hat j acting on x hat I acting on vi2 through vit is equal to delta ji minus delta ji, I should write this on a new line, equals, it's kind of weird notation, but whatever, minus delta ji times ci2I plus through the Cartesian integer of iti, scaling vi2 through vit, which is just delta ji on h hat I on vi2 through vit. And if you notice here, the start looks like the Lie bracket of xi and yj acting on this series. And what we're left with is delta ji times h hat of I. Now, we also need to see that this works on constants. So x hat I, y hat j, minus y hat j, x hat I, on 1. I mean, all of these is going to be set. X sets both constants, y turns constants to single variables, and x turns both constants and single variables to 0, so this is going to be 0, which is delta ij times hi norm on 1. Thus we get that the bracket of x hat I, y hat j, minus delta ij, h hat I, is inside k hat of 0. Next, we see that h hat I, y j, a hat j minus their switcheroo on 1 is h hat I on vj, which is negative cji vj, which is negative cji yj on 1. Similarly, h hat I, y hat j minus y hat j, h hat I on vi1 through vit is h hat I vj times vi1 through vit plus the sum of our Cartan ci1i plus through citi, scaling up vj times vi1 through vit, giving us negative cji of y hat j on vi1 through vit. Therefore, we get that the bracket of h hat I and y hat j plus cji y hat j is within k hat 0. And the last one is a bit difficult to calculate, so we need a pre-calculation that notice h hat I on x hat j and vi1 through vit is equal to negative of the sum of the appropriate Cartan indexes through citi minus cji times x hat j on vi1 through vit, which can be shown by induction on T with T equals 0 giving both sides as 0. For the induction hypothesis, this says that x hat j of vi2 times through vit is an eigenvector of h hat I with eigenvalue negative ci2i plus through citi minus cji. Multiplying this eigenvector by vi1 on the left gives an eigenvector for h hat I with eigenvalue of the same as before, except we add in ci1i plus citi minus cji. And from this, we finally calculate our last theorem. Hi xj minus xj hi on 1 is 0. H hat I x hat j minus x hat j h hat I on vi1 through vit is equal to, once again, I'm going to need a new line, minus ci1i plus through citi minus cji plus ci1i plus through citi x hat j on vi1 through vit equaling cji x hat j on vi1 through vit. So the bracket of h hat I with x hat j minus cgi x hat j lies within k hat 0, and we finally get every case And so our k hat lies within k0 hat. So give me 1 second here. Theorem. Another theorem here. Given a root system with base alpha I from 1 to L, let L0 be the Lie algebra with generators of xi, yi, zi, index 1 through L, of course, and relations 1 through 3. And then the HI are a basis for an L-dimensional abelian subalgebra H of L naught, and L naught is equal to the direct sum of y plus h plus x, where y and x are of course generated by the generators y and x. In the proof, we're going to use the previous representation we constructed phi from L naught to GLV as above, with phi of x being equal to phi hat of x hat if x is the image of x, some variable x hat in L hat in our L0. Our first step is that the sum of our field times the h hat of j intersected with the kernel of our phi is 0. If h hat is the sum from 1 to L of aj h hat of j, and phi hat of h hat equaling 0, then the eigenvalues of the minus sum of over j of aj cij of phi hat of h hat are all 0. But the Cartan matrix is not of phi, of course, is non-singular. So all aj in this case is 0, so h hat is 0. The canonical map from L hat to L0 sends the sum of f h hat j isomorphically onto the sum of f times h of j, and this is just like immediate, given that the kernel is the intersection with the kernel is 0. The subspace the sum of f x hat of j plus the sum of f times the y hat of j plus the sum of f times h hat of j this as a subspace of L maps isomorphically into whatever L0. So we're going to fix an I as from our relations the bracket of xi by I equals hi, bracket of hi xi equals 2xi, and the bracket of hi yi equals negative 2 yi. Then we see that fxi plus fyi plus fhi is a homomorphic image of SL2 of f, which is simple. As we saw in step 2, that hi is non-zero. fxi plus fyi plus fhi is isomorphic to SL2 of f. So a set of xi, yi, j, hi is linearly independent. So that gives us step 3. For h is equal to the sum of fhj and is an L-dimensional abelian subalgebra of L0. And once again, this is immediate from the previous. Step 5. So we're going to write, I'm just going to write it out properly. The bracket of hj on the bracket of xi1 on the bracket through xit. You understand what's going on there. Is equal to the sum of the carton I1 j plus through carton IT of j times xi1 on the bracket of xi2 on the bracket of all the way into xit. And negative this negative for y instead of x. This is by induction from our relation 3 is our base case, and the Jacobi identity. Alright, 3 more steps to go. Step 6. If t is at least 2, then yj on xi1 through xit is within x, and of course similar for y. By relation to sorry, I'm trying to keep track of things here. The bracket of yj on xi is negative delta ij on hi. So t equals 2 is the Jacobi identity. And then we go by induction on t. Theorem 7 is that y plus h plus x, I don't know if the order matters, but I'll copy it anyways, is a subalgebra of L0 and hence coincides. Is a subalgebra from the previous 3 steps and contains generators of L0. Step 8, L0 equals y plus x plus h plus x is direct. This is from step 5 mostly. And then on eigenspaces, you can decompose it into eigenspaces for the adjoint of H. That's the end of our proof. One last note, we may describe this decomposition in terms of weights. For lambda in H star, let L0 lambda be the set of T and L0 where the action of H on T is lambda H times T for all H in H. Then H is L0, 0. Let's see, the only non-zero lambda with L0 lambda being non-zero are the lambda of the sum of ki alpha I for ki in the naturals with 0, or negative ki in the naturals with 0. Then x is the sum of the positive lambda L0 lambda. Y is the sum for negative lambda of L0 lambda. And I think that'll be it for today's video. We're kind of going over time consistently here, but that's how it goes sometimes. You know how it is.